Hello everyone. And today we're going to oh, you should see my screen, right? Rather than my face, right? So or a little version of my face, anyways. Okay. Today we're going to do analysis of functions. So ultimately, the final goal is to be able to look at the function, understand how it behaves, and then being able to sketch the graph. Now, we live at a time, well, when I was a student, that was completely unavailable to me, where you can just type in any function and it will draw it for you. But nevertheless, if you go to do some entrance exams to university, some such as TMUA or like it was PAT or MAT, or you go to a university interview, they will ask a lot of questions about drawing graphs. So they will give you a function, which hopefully you haven't seen before, and they'll ask you to sketch it. And you need to understand how functions behave based on a few features. So today, I'll make a list of the things that you need to look at when deciding um, how a function behaves. So, features of functions. So, I'll try not to forget anything. There's so many. Well, first of all, range and domain. Range, domain. Then you would want to look at zeros and intercepts. Continuity. Is the function continuous, or does it have breaks? Like the hyperbola, like 1 over x has the breaking point 0. Yeah, so it has a point where it doesn't exist. Continuity, you're interested in continuity with then behavior at points of discontinuity of discontinuity. And behavior at infinity. Behavior at infinity. If infinity is in the range, in the domain, of course. Then asymptotes. Asymptotes, which are horizontal, vertical, slant. Right. So what else? Well, I haven't even touched derivatives. Yes. So increasing or decreasing, and that's you look at the derivative of the function. If the derivative is positive, then it's an increasing function. If the derivative is negative, it's a decreasing function. Then concave, convex, and this is you're looking at the second derivative. So if the function is increasing, that means the first derivative is positive, and the function is decreasing, the first derivative is negative. Concavity. So this is concave. That's when the second derivative is negative. Concave. And convex. Convex is when the second derivative is positive. Right? What else? Yeah, and once you've looked at some of these features, you don't have to look at all of them. You choose some of them. And once you've chosen enough features to understand the overall behavior of the function, then you can sketch it. And it is some form of art, I think. honestly. Um, so today we'll be looking at different functions, different approaches, and hopefully you just get a sense of how to approach with an unknown function, what to do with it. And some of the questions will have some guidance, some questions won't. So let's just jump in. So problem one, state the domain and range of each function. Okay, so f of x equals square root of 4 minus x squared. Now, the domain is the possible values of of x. So here the limitation is that 4 minus x squared must be greater or equal to 0, because you can't take the square root of a negative number, and that means that x squared must be less than or equal to 4, or rather x squared minus 4 is less than 0, x minus 2, x plus 2 must be less than or equal to 0, and therefore you write minus 2, 2, so it's positive, positive here, and yeah, so x belongs to from minus infinity to negative 2, including, or from 2 to plus infinity. So this is the domain of that function. Oh, sorry. What am I doing? Silly me. It's negative. You need the negative parts. Right, so you need the negative part, so that is this bit from minus 2. X belongs from minus 2 to 2. Right, so x can only take certain values, and then square root of 4 minus x. Well, would you find the range? Well, technically, to find the range, you would need to find the maximum point, right? So to find range, find maximum point, maximum and min values, and then you differentiate f dash of x is equal to minus 2x multiplied by 1/2 multiplied by 4 minus x squared to the power minus 1/2, and then you equate that to 0, then x equals 0 is the critical point. And also and that's it. Yeah, x equals 0, because all right, x equals 0, and then f of x of 0, and if you sub that in, you would get 2. Square root of 4 minus 0 squared is 2. So the max value is 2. And f of minus 2 is 0, and f of 2 is also 0. So you kind of can get a glimpse of the function, like how it actually looks like. So x can take values between minus 2 and 2. And then y can take values from 0 to 2. From 0 to 2. Right, and well, it's going to be like this. That's the only maximum point. You can verify that the second derivative, let's not go there. Let's not. We'll touch the second derivative later on. We don't really need it. We don't really need it at the moment. Yes, that's the strict way of how to do it. But you could also just look at this. Well, square root of 4 minus x squared. Well, x squared is always positive, right? X squared always positive. So 4 minus x squared has is maximum, is max when x is 0. You could always do that. It's just like, oh, when x is 0. When x is 0, it's 4. If x is 0, f of x, f of 0 is just 2. Okay. Another way, you could always do this. Y equals square root of 4 minus x squared. Square both sides. Y squared equals 4 minus x squared. And then x squared plus y squared equals 4. It's a circle. So it's a semicircle because y cannot be negative, of course. All right. Okay, so we've done this one. And then the second one, f of x equals square root of x squared minus 4. Now, this is a slightly different story. So domain, x squared minus 4 must be greater or equal to 0. So x minus 2, x plus 2 must be greater or equal to 0. So minus 2, 2. And that's positive, positive, negative here. So we're interested in these values. So x takes values from minus infinity to negative 2, or from 2 to plus infinity. X belongs to the set from minus infinity to minus 2. And then, well, the minimum value, then you just look at x squared minus 4. Well, x squared minus 4, because x, well, it can't be 0. It first of all has to be greater than 0, right? And then, but there's no upper limit because smallest value when x is 2, and then you go to infinity as x tends to infinity, y also tends to infinity. So it is unbounded. So y belongs to from 0 to plus infinity. Okay. And another trick that you can do here is behavior at infinity. At infinity. So what can you do? Well, you can say that x squared minus 4 for large values of x, for large values of x, x squared minus 4 is pretty much x squared, right? I mean, a million squared and a million squared minus 4 is pretty much the same thing, right? Like this car uh, this car doesn't cost £100,000. This car costs £99,999 and 99 pence, right? So x squared minus 4 is the same as x squared, right? Is that clear? And therefore, square root of x squared minus 4 is pretty much the same as square root of x squared, which is pretty much which is well, actually, it's modulus x. Yeah. And so for large values of x, the function so the function behaves like x squared. So that's the slant asymptote. That's a slant asymptote. So you draw the modulus function, and you say, well, if this is 2 and this is -2, we know that the values it's 0, 2, 0, and -2, 0, and then the function is increasing. So it's like this. It approaches, for large values of x, it approaches y equals modulus x. Okay, so on one graph, as they were asking in one graph, it's just two dots. Let's choose a different color. So that's the previous graph. This one. All right, and what do we need to explain? Explain why one represents a bounded function, the other does not. Well, it's obvious. This is it is bounded because f of x can be put between two values where a and b are real numbers. That means that's what bounded means. Bounded means that the function takes only values between two real numbers. Whereas here, y, well, f of x is greater or equal to 0, so it's unbounded. Unbounded, yeah. Okay, so hopefully that makes sense, and let's move on. The next question is a bit weird. I was thinking maybe I shouldn't include it, but it's fine. So you find the composite of fg. G of x is, so you just put g into x. So it's going to be 3x3 multiplied by x minus 1 over 2x plus 3 minus 2 over x minus 1 over 2x plus 3 plus 1. Right, and let's see where that takes us. That takes us to 3x minus 3 minus 2. You multiply this by 2x plus 3, and you multiply this by 2x plus 3. Effectively, you're multiplying top and bottom by 2x plus 3. And that's minus 4x minus 6. And here we have x minus 1 plus 2x plus 3. And that is minus x minus 9 over 3x plus 2. Okay. Then find fg or f and simplify. So we've done that. That's A. State the domain of fg of x. Well, the domain is that x is not 2 over minus 2 over 3. X is not minus 2 over 3 because then you're dividing by 0. But also, because this is a composite of f of g, you have to take into account that x is not minus 3 over 2 because it's 0 at that point. X is not minus 3 over 2. You need to remember that. Because even though this expression exists at minus 3 over 2, the original function doesn't, so the composite doesn't exist either. And therefore, so this is the domain. Determine all vertical and horizontal asymptotes. C. So to do vertical asymptote is very simple. Asymptote. is when the denominator is 0. So 3x plus 2. No, because you're not substituting x into f. You're substituting g into f. So effectively, you're having 3g minus 2, g plus 1. So g is not equal to -1. But we already know that g is not equal to -1 because, well, it can't. So no, the answer to your question is no. Sorry, I don't know what's happening with Miro today. Vertical asymptote is when the denominator is 0, and that means x, 3x is -2, x is -2/3. So that's the vertical asymptote. To find the horizontal asymptote, what you need to do is find the limit. So y is the limit of x tends to infinity of that minus x minus 9 over 3x plus 2, and to find this limit, you would you divide top and bottom by x, and you get minus x minus 9 over x over 3x plus 2 over x, limit x tends to infinity, limit x tends to infinity, minus 1 minus 9 over x. Name for this method. I am unaware that method has a name. Well, the definition of a horizontal asymptote. That's the definition of a horizontal asymptote. The horizontal asymptote is the limit of the function as x tends to infinity, if that limit exists. And that's the 3 plus 2 over x. And now as x tends to infinity, because x becomes really big, this thing becomes 0. And so does this becomes 0. So the limit is -1/3. So y equals -1/3 is a horizontal asymptote. -1/3 is a horizontal asymptote. Horizontal asymptote. Horizontal asymptote. Okay, and then we can start sketching the graph. So we have the horizontal asymptote, -1/3. Okay. We have the vertical asymptote, which is -2/3. -2/3. And then what do we have? Do we have the zeros? Zeros. So minus x minus 9 over 3x plus 2. So the 0 is x equals -9 is a 0. Okay, so -9. And when x is 0, intercepts a y-intercept. So f of 0 is -0 minus 9 over 3 times 0 plus 2. And that is -9 over 2. -4/5. So that is negative Negative 4.5. Negative 4.5. Okay, let's go a little bit further. Even though you probably know how the function looks like because you recognize this function, but let's do some more stuff. So let's find the derivative. So f dash of x, and f dash of x is minus x minus 9 over 3x plus 2 dash, and that is minus 1 multiplied, well, minus 3x plus 2 minus x minus 9 multiplied by 3 all over 3x plus 2 squared. And if you simplify that, minus 3x minus 2 plus 3x plus 27. 3x cancels. And we get 3x plus 2 squared. And that is 25 over 3x plus 2 squared. Now, this value is never 0, and it's always positive. Because 25 divided by, it's always a positive number. It cannot be negative, and it can't be 0. Therefore, f of x is always increasing. So it's always an increasing function. F dash of x is greater than 0, right? Well, you could find the second derivative. Yeah, let's do that. The second derivative, f double dash of x. To do this, I'm going to do 25 3x plus 2 squared minus 2 dash. So the second derivative is 25 multiplied by negative 2 multiplied by 3x plus 2 to the power negative 3 multiplied by 3. Have I made a mistake somewhere? Because I shouldn't have this. I shouldn't have a cubic. Oh, no, that is correct. Yes. So that is negative 150. Yeah. Over 3x plus 2 cubed. Right. So when is the second derivative negative? So if x is greater than negative 2 over 3, you can see that, then the second derivative is negative, and therefore it is concave. Concave when x is greater than negative 2/3. And if x is less than negative 2/3, then this value is negative. The denominator is negative, so the second derivative is positive. So it's convex. Convex when x is less than negative 2/3. So we can sort of draw that. So it's concave and it's convex and increasing. So until negative 2/3, because and that's a vertical asymptote. Until 2/3, it's convex and increasing. So it's like this, convex and increasing. And from minus 2/3 is concave and increasing. And that makes perfect sense. So this is convex increasing. And this is concave increasing. All right, so there's so much information we can get, right? So we basically It is a hyperbola, of course. Of course, it's a hyperbola. We already knew that, but it's nice to see that verification once again. So the function goes like this, and here goes like this. Although there's a big catch. Remember that x is not equal to -3/2. So -3/2, that's somewhere here, -3/2. The function does not exist, and we have to put that in. It's a round dot with two arrows, and this is called a undefined. Undefined. That's important, right? Okay, so that's it. You can see that happening. Like, look, if you take Desmos and draw a function, something like y equals open bracket x minus 2 squared divided by x minus 2. It seems like it's a straight line. Well, it is a straight line, so sorry. It doesn't seem like it's a straight line. But the function doesn't exist at x equals 2, because at x equals 2, you're dividing by 0. And what does Desmos do? It tells you that, okay, if you're lucky, that 2 undefined. All other points exist, like 0 minus 2, but 2 is undefined. So it's how to show break in the curve on sketching on paper. Exactly the same way. You show you draw a parabola, circle like this. So you just say that this point is undefined. I think it's called the discontinuity of the first type. Discontinuity of the first type, where it's a removable discontinuity. Removable discontinuity. Okay. Now let's look at these. Oh, of course, odd or even. I forgot about that. Behavior odd or even. Because when you arrange them in odd, even, that's the first thing you look at. Is in an odd function or an even function. Determine whether the following functions are even, odd, or neither. Justify your answers. So very straightforward. So f, what you need to do is find f of minus x, and this is minus x cubed minus 4 minus x, and that's equal to minus x cubed plus 4x, which is the same as minus f of x, and that means it is odd. F of minus x is minus x squared multiplied by sine minus x, and that is x squared, because minus x squared is x squared, multiplied by minus sine x, which is minus x squared sine x, which is minus f of x. So that's an odd function as well. Right? C mod f of minus x is modulus x cubed minus x cubed. And we know that modulus minus x is the same as modulus x. The modulus minus x is the same as modulus x. Therefore, it is the same as x cubed, modulus x cubed, which is the same as f of x. So that means it's even. Does everyone know the definition of odd and even functions? I don't need to explain, right? If you don't, let me know. Happy to do that. And D is y is f of minus x. So we substitute if. Okay, yeah, happy to. So a function is f of x is odd if two things are true. Domain is symmetrical, and two, f of minus x is equal to minus f of x. And then if f of x is odd, the graph has rotational symmetry or point symmetry, a tree over the origin. Okay, so for example, f of x equals x cubed is odd. So how do we know it's odd? Because if we sketch it, it looks like this. Okay, so first of all, the graph has rotational symmetry. You can see that if you flip the graph upside down, it's the same graph. And then if you take this is x, and this is f of x, and this is minus x, and this is minus f of x. So I repeat myself, f minus x must equal to f minus f of x. Effectively, you can take the minus out of the function, and that's an odd function. An example is a sine function. Sine of minus x is minus sine x. That's odd. Minus x cubed equals minus x cubed. That's odd. Okay, hopefully that makes sense. Now, if you f of x is even, f of x is even if two things are true. Domain is symmetrical. And two, f of minus x is equal to f of x. The graph of an even function, has line symmetry over the y-axis. Right, so y equals x squared is symmetric, is even because f of minus x is minus x squared, which is the same as x squared, which is the same as f of x. And the graph is symmetrical. You can see that the value at x is exactly the same as the value at minus x. So that's f of x. So they're both symmetrical. So f of x is equal to f of minus x. That is the symmetrical graph. And also the domain has to be symmetrical, because if you take just half of the parabola, it's not an even function. And then cosine x, cos minus x is cos x. So that's even. X minus x to the power 4 is the same as x to the power 4. So that's even, etc. Modulus x. Yeah, modulus x. Modulus minus x is modulus x. So that's even. Okay, so moving on. You find f of minus x here. So that's going to be cos of minus x minus 2. And that's not equal to minus f of x. And neither it is equal to f of x. So it's neither. Neither. And you can sketch the graphs to actually verify that. So the first graph is x cubed minus 4x. So it has 0 and 4. 0. Something's off. Oh, 2 and minus 2, of course. 2 and minus 2. So the first graph is like this. Minus 2, 2, 0. Is minus x to the power n? Yes. Yeah. Minus x to any power. Minus modulus of minus x to the power n is even. Yes. The second graph is x squared times sine x. Well, x squared times sine x is like this, so it's and here. Something like that. And this graph is modulus x cubed. So that's just that. Modulus x cubed is a graph like this. Modulus x cubed. And cosine x minus 2. Well, it's neither. It's x minus 2, so it's x cosine x shifted by 2. So say 2 to the right. So that's 2, 1. And then something like that. So no, it's not symmetrical. It doesn't have a line symmetry, and neither it has a rotational symmetry, because at 0 it's this. Okay, moving on. The function is defined for all real x's. Find the derivative. Determine the stationary points and classify them. Here the graph has a line of symmetry. Oh, interesting. Determine whether it has a line of symmetry. Well, let's see. F dash of x is 4x cubed minus 24x squared plus 36x minus 16. We need to find the stationary points. Stationary points is when the derivative is 0. So we make that equal to 0. So 4x cubed minus 24x squared plus 36x minus 16 equals 0. Divide by 4, x cubed minus 6x squared plus 9x minus 4 equals 0. So what can we guess? 1. Does 1 work? 1 minus 6, 1 minus 6 is minus 5, plus 5. Oh, x equals 1 is a solution. X equals 1 is a solution. So I'm going to factorize. And to factorize, I'm going to do it like this. X cubed minus x squared minus 5x squared plus 5x plus 4x minus 4 equals 0. So what I've done is I've broken the 6x squared into this. I've broken 9x into this. And look what happens when I do that. From the first two, I can group them. And the first two, I extract x squared as a common factor, and I'm left with x minus 1. For the second pair, I take out minus 5x, and I'm left with x minus 1. For the third pair, I just take out 4, and x minus 1 equals 0. So x minus 1, open bracket, x squared minus 5x plus 4 equals 0. X minus 1, I can factorize this straight away. So that's x minus 1 and x minus 4 equals 0. So x equals 1 and x equals 4 are stationary points. Stationary points. And then I can determine their nature. So to determine to classify them, I find the second derivative. Second derivative of x is 12x squared minus 48x plus 36. And then I say the second derivative at point 1 is 0. That means x equals 1 is a point of inflection. And f double dash of 4, that's 12 times 16 minus 48 times 4 plus 36. 12 times 16 is the same as 48 times 4. So they cancel out. And so that's greater than 0. So x equals 4 is a minimum point. Minimum point. How do I know it's a minimum? Well, because the second derivative is positive, that means it's a convex function. And if a convex function has a stationary point, that means it is a minimum. So the second derivative is positive, and the first derivative is 0. This is a point of inflection. So we have the first derivative is 0, but the second derivative changes sign, is also 0. So here we have a x equals 1. So that's decreasing and then decreasing again, I'm guessing, because the second derivative. So this is minus 1. So 1, sorry. Yeah, decreasing. So that's where the first derivative is 0. The second derivative is also 0. That's the point of inflection. Lovely. Okay. So I can sort of draw this graph. So we have two interesting points, 1 and 4. Well, I would probably need to find f of 1 and f of 4. F of 1. To make sure it's a point of inflection, do you need to check concavity? Yes and no. Yes, to be sure that it is an inflection point, you have to change. Well, no. So it's an inflection point if it's if the second derivative. Oh no. Yeah. Yes, you are correct. To make sure it is a point of inflection, you do need to check concavity. However, if you're talking about A-level questions, so if you're doing A-level, then they will not give you a situation where the second derivative is 0 and it's not a point of inflection, because that would be just too cruel. So in A levels, if the second derivative is 0, it is a point of inflection. So you need to worry about that. I hope that answers your question. So f of 1, you just need to find the value at 1, so the y value. So 1 minus 8, 1 minus 8 plus 18. I'm already dreading substituting 4 minus 16 plus 5, and that is 10 minus 6. Oh, it's actually 0. Oh wow, that's interesting. So not only it is also just 0. Okay, f of 1 is 0, so that's the point. And f of 4, and we just substitute 4, 4 to the power 4. 64 to the power 4. Isn't it just 256? 256 minus 2 times 512. Okay, not too bad. Plus 18 times 16. 18 times 16. Minus 16 times 4. So 64. Plus 5. I don't think I can do that in my head. Well, I can, but I'm not in that state of mind at the moment. 18 times 16 minus 64 plus 5, negative 27. Right, so negative 27. So 4, negative 27. That's the minimum point. We already know that. That's an inflection point. And we know that the function goes like this. Then it goes like, so this is an inflection point. It goes through 0, 5 as well. 0, 5. So something like this. And we can definitely tell that this has no lines of symmetry. Lines of symmetry. And this is proved by the graph, right? So if it has a line, so there are different arguments you could use. You could say if the line of symmetry goes through the point 1, that means it has to have a minimum point on either side. So if it had a line of symmetry, it would have to go through one of the interesting points, because there's only one inflection point. Therefore, it has to pass through the inflection point. Because if the line of symmetry doesn't go through the inflection point, then you have to have 2 inflection points, if that makes sense. So if this line of symmetry goes through the inflection point, then you have to have 2 minimum points. And vice versa. If the line of symmetry goes through well, as a matter of fact, the line of symmetry cannot go through the inflection point, because if it goes down on one side, it has to go up the other side. So a line of symmetry can only go through the minimum point. But if it goes through the minimum point, it has to have 2 inflection points on either side, because it has to be symmetrical. So no. That's one way of arguing it. The other one is just, well, look at the graph, and there's no lines of symmetry. All right, so hopefully that makes sense. Okay, how are we on time? Consider the function x e to the power minus x. Oh, I love this function. Oh, this is one of my favorite ones. When I do this function, I just say, just use your common sense. So what do we know? What do we know about them? Well, we can sketch them both. So I'm going to try a different approach. I'm going to sketch the both graphs. So the first graph is like this. So it's very big. It's very big for positive values, very small for negative values. And the second graph is, of course, we all love it. We all know it. It's e to the power minus x. It's this. So this tends to 0, this tends to 0, and this tends to plus infinity. And this tends to plus infinity. And this tends to negative infinity. Right. When you multiply them together, well, you can see, first of all, it's positive when x is greater than 0, they are positive. Because this graph is always positive. So when the first graph is positive. So note, if x is positive, then y is positive. By y, I mean y is, okay, not that, f of x. Let's just use f of x. If x is 0, f of x is positive. If x is negative, f of x is negative. Now, infinity times plus infinity times negative infinity is negative infinity. So when as x tends to negative infinity, f of x tends to negative infinity. Okay, that's nice. At x equals 0, f of 0 is 0. That's another note. So it goes through 0. So what do we know? So we know that it goes through this point. It's positive here. It's negative here. So at negative infinity, it goes really, really big. So it goes infinity. Now for positive values, as x goes to plus infinity, what you need to note is that x divided by e to the, because that's e to the power minus x multiplied by x equals x over e to the power x. E to the power x is much, much, much bigger than x. E to the power x is much greater than x. And therefore, for positive values of x, it tends to negative infinity. So it tends to 0. As x tends to plus infinity, f of x tends to 0. And another thing, for small values of x, for small values, for small positive values of x, e to the power minus x is approximately 1, and therefore e to the power minus x multiplied by x is approximately x. So the function behaves like x. So it just behaves like this at the beginning. And then something changes and it goes like this. So this is the way I like to look at it. So it gets really, really negative and then goes through the point, and then it follows the y equals x, but then e to the power x becomes more powerful and it drags it down. I really like to think of functions in that way. So once again, so f of x equals x multiplied by e to the power minus x. So you can see that for small, when x is small, This is just 0, 1, and the function behaves as x. Okay, let's see if that makes any sense. Y equals x multiplied by e to the power minus x. And yeah, it does. Okay. So it just behaves like an exponent on the left. Then it goes through 0. It has a maximum point, and then like that. And let's see if we can do the same thing, but analytically rather than doing educated guesses on the behavior. Right. So let's find the first derivative. So a f dash of x, and so that's 1. So using the product rule, 1 multiplied by e to the power minus x plus x multiplied by minus e to the power minus x. And so that's e to the power minus x, 1 minus x. Now, e to the power minus x is always positive. And that means that e to the power minus x, 1 minus x, is positive. If 1 minus x is positive, that means x is less than 1. So, increasing, seeing when x is equal to 1, and then decreasing, seeing when x is greater than 1. Right? And then you can find the second derivative, and that's going to be minus e to the power minus x minus e to the power minus x plus x multiplied by e to the power minus x. Yes. So that is e to the power minus x, x minus 2. And then you can see when is it e to the power minus x, x minus 2. So that's greater than 0. So x is greater than 2, and it is convex when x minus 2, concave when x is less than 2. Okay. So I also like to do this. So I draw the domain. I put some interesting points. So 0 is an interesting point. So 0 is an interesting point. Then 1 is an interesting point, and 2 is an interesting point. So I know that the function is negative here, is positive here, and positive here. Now the first derivative is positive here, negative here, negative here. The second derivative is negative here, negative here, negative here, and positive here. And we can talk about the behavior. So if the function is positive, negative, and it's increasing and it's concave, so it goes like this. It's below the x-axis. It is increasing and it's concave. Now, between 0 and 1, it's positive, it's increasing, and it's concave. So it's like this. From 1 to 2, it's decreasing, it is concave, and it's positive. So it goes like this. And then from 2 to infinity, it is decreasing, it is convex, and it's positive. So it goes like this. And that gives you a really good idea how the graph looks like. Or you also need to do f of 1, of course, f of 1 and f of 2. So f of 1 is just 1 over e. 1 over e is approximately 0.37. And f of 2 is 2 times 2 over e squared. 2 over e squared, which is smaller than that. So we have 0, 1, and 2. 1 and 2. So 1 is 1 over e. 2 is 2 over e squared. And here, so it's increasing like this. This is a maximum point. And this is a point of inflection. Yes. Right. X. So that's inflection. Now, note that for a point of inflection, inflection only means the second derivative is 0. Second derivative is 0. It does not mean that the first derivative won't be 0. First derivative can be anything. I think I've mentioned this here and I wasn't clear. Point of inflection, you don't have to, this doesn't have to be true for a point of inflection. Inflection is where the concavity changes. That's all. That's all what a point of inflection is. Change of sign of the second derivative. Yes, the concavity changes. Yes, that's what it means. Cool. This table is incredibly useful because it actually tells you the behavior of the function on different intervals. And we'll be using that in the next assignment on the method of intervals. So you will see how powerful this method is. Okay, consider a cubic function. Show that the x-coordinate of the point of inflection depends only on a. Oh, did we complete the task? Do you have any look on maximum minima? Yeah, so 1 over e, that's a maximum. And we've done that. And so this is maximum. This is a 0. And this is an inflection. Okay. F dash of x is 3x squared plus 2ax plus b. And second derivative of x is 6x plus 2a. And yes, inflection point is where 6x plus 2a is 0. So x is a over 3, negative a over 3. In the coordinates of the point of inflection, so f of minus a over 3 is going to be minus a over 3 cubed plus a multiplied by minus a over 3 squared plus b multiplied by minus a over 3 plus c. That's a weird question. Minus a cubed over 27 plus a cubed over 9 minus ba over 3 plus c, which is 2a cubed over 27 minus ba over 3 plus c. That's a coordinate of inflection. State the conditions on a and b for the function to have two distinct turning points. Two distinct turning points. Well, two distinct turning points is when the second, well, the first derivative is 0. So that's question A. B. So B is minus a over 3 and 2a cubed over 27 minus 6ba over 3 plus c. That's inflection. And C. State the condition on A and B. So we have the quadratic. So 3x squared plus 2ax plus b equals 0. That's the derivative of stationary turning points. And then we have just the discriminant is b squared. So it's well, 2a squared minus 4 multiplied by b multiplied by 3. And so that's equal to 4a squared minus 12b. So that's the determinant, and it has to be greater than 0. So 4a squared minus 12b must be greater than 0. So a squared minus 3b must be greater than 0. So a squared must be greater than 3b. That's the... What is that symbol? What symbol? Sorry. Oh, D. Discriminant. Yeah, so that's discriminant. The symbol is D. D is just a squiggly D. Sorry, how I was taught in school. Yeah, it's just a D. Right. Cursive D. Cursive capital D. Yeah, here it is. Okay. D. Anyways. You also it also x must not equal to a over 3, so I don't know if that makes any sense. X is minus 2a plus minus square root of 4a squared minus 12b over 6a. 6 over 6, sorry. Oh, okay. So this must not equal to negative a over 3. So that simply means that the discriminant must not equal to 0, and it doesn't equal to 0 because we already said that. It's strictly greater than 0, so that's fine. Problem 7. Analyze and sketch the function Your analysis should include domain, intercepts, vertical and horizontal asymptotes, behavior near asymptotes. Right, so we have that's an interesting one. So domain x is not equal to plus or minus 2. So it seems like +2 and -2 are vertical asymptotes, but we have to double check to check whether a point is a vertical asymptote. What we need to do is find the limit as x tends to 2 of x plus 2, x squared minus 4. And that's equal to the limit of x plus 2, x minus 2, x plus 2. And x tends to 2. And as x tends to 2, you can see that tends to infinity. So that means x equals 2 is a vertical asymptote. So at a point of vertical asymptote, the function has to go to infinity. And now if you do limit as x tends to -2, which is x plus 2 divided by x minus 2, x plus 2, cancel, and it gets -2, so it gets limit of 1 over x minus 2 as x tends to -2. But that is not 0 and not infinity. That is actually -1/4. So not infinity. That means that x equals -2 is not a vertical asymptote. So the function only has one vertical asymptote, and that's x equals 2. That's nice. So x 2. Horizontal asymptotes. So intercepts. So if x is 0, then y is a -1/2. 0 -1/2. So that's this point, -1/2. And then if y is 0, then x is -2. But -2 is not the domain. Not possible. But it is a point of, we call it discontinuity. We know that as x tends to -2, it's what? Oh, as x tends to -2, it's -1/4. All right, so -1/4. So this point. We know that we know the limit as x tends to -2 is -1/4. So it's this point, but the point is undefined, but the limit is -1/4. And then this is a vertical asymptote. And then as x tends to as x tends to 2 plus 0, that means it tends to 2, but from the right hand side, and that becomes x plus 2 over x squared minus 4, and that becomes plus infinity. And the limit as x tends to 2 minus 0 So approaching 2 from the left is x plus 2 over x squared minus 4, x squared minus 4, and that's minus infinity. So it goes, and at, what do you mean approaching from right to left? Well, the function can be approaching 2. Well, we're looking for the limit as x tends to 2. But what do we mean to 2? Is it approaching from here, from the right, or approaching from the left? Because it could be very different result. So when we say approaching from the right, we write 2 plus 0. Okay, so as x tends to 2 plus 0. So x getting closer and closer to 2, but it still remains more than 2. And if we do that 1 over x minus 2, you can see that it does approach 0, but it still remains positive. So 1 divided by plus 0, so it's 1 divided by plus 0, which is plus infinity. And when you're finding the limit as x tends to 2 minus 0, so it's approaching from the left. That means it is getting closer and closer to 2, but it remains less than 2. And if it remains less than 2, then this number is 1 over minus 0, which is minus infinity. As x tends to 2 to the power plus 2 plus. Yeah, I think so. Yes, 2 plus. Yes. I haven't seen that notation, but we say plus 0. Maybe there's a different way of writing it down. Um, I think you're correct. And then as x tends to infinity, at the limit, as x tends to infinity, to plus infinity, of x plus 2 divided by x squared minus 4, well, that's 0. Okay, so that's like this, and this is like this, and that's discontinuity. Continuity. Behavior near asymptotes. Yes. So that's what we've done. Yes. Yeah. That's exactly that's what it is. You're correct. Find the range of the function. Is it different? Oh, okay, it's a different one. I haven't talked about slant asymptotes. But why is not 0? Why is not 0 when x equals negative 2? That's why I said it's not possible. Why x is not negative 2? Because x plus 2 divided by x squared minus 4, if you substitute 2, x equals negative 2, then you get minus 2 plus 2 divided by 4 minus 4, which is 0 divided by 0, so that's undefined. Undefined. It's definitely not 0. Okay. What I haven't spoken about is slant asymptotes. And I wonder if I should talk about slant asymptotes instead of the last question. Yeah. Yeah, let's not do this one. Slant asymptotes. Asymptotes. Slant asymptotes, well, if you look at some functions like x squared plus 3x plus 2 divided by x minus 7. It has a slant asymptote. And we can sketch that. Y equals x squared minus 3x plus 2. X squared minus 3x plus 2. And divided by x minus 7. X minus 7? Yes. So this graph has two asymptotes. One is a vertical asymptote and one is a slant asymptote. So this is actually x equals 7. That's an easy one. But what is the equation of this asymptote? Well, the easiest way to find a slant asymptote is the following. You need to break it down into two fractions. So basically, you need to use long division. To find a slant asymptote, use long division. To find a slant asymptote, use long division. So literally, you just need to divide the top by the bottom. Although there's an easier way. F of x equals x squared minus 7x, because that's what we need, plus 10x plus negative plus 10x negative 70 plus 72. So what I've done, I've just rewritten. I've rewritten the top in such a way that it divides by x minus 7. Well, the first two divide by x minus 7. I don't care about the rest. This is the remainder. And this is x multiplied by x minus 7 plus 10x minus 7 plus 72. And they divide by x minus 7. And now I divide. So I break it down into three fractions, and it becomes x plus 10 plus 72 over x minus 7. And this is my slant asymptote. Slant asymptote. Y equals x plus 10. So the equation of that line is y equals x plus 10. How do I know that? Well, just look at it. This is the function. And as x, when x is large, when x is large, 72 over x minus 7 tends to 0. This term is 0 because as x becomes bigger, this is 0. So f of x is approximately, well, f of x, which is x plus 10 plus 72 over x minus 7, is approximately the same as x plus 10. That's why it's a slant asymptote. This is the easiest way to talk about slant asymptotes. You normally have a slant asymptote when the power of the numerator is 1 more than the power of the denominator. Yeah, that's about it. That's about it for slant asymptotes. Like, let's see if we can do another one. Running out of time. So f of x equals okay. Rather than Uh, I'll give you a more formal definition. Formally. If y equals mx plus c is a slant asymptote, then m is the limit as x tends to infinity of f of x divided by x. And let's check if it works. The limit of x squared plus 3x plus 2 over x minus 7 divided by x as x tends to infinity. So that's the limit of x tends to infinity of x squared plus 3x plus 2 divided by x squared minus 7x. Divide top and bottom by x squared, and that's the limit as x tends to infinity of 1 plus 3 over x plus 2 over x squared. 1 minus 7 over x and you can see that this tends to 0, this tends to 0, and this tends to 0, so the limit is 1. And m is in fact 1. Yes, so m is 1. And then c is equal to the limit as x tends to infinity of f of x minus m multiplied by x. Okay, let's check. So the limit as x tends to infinity of x cubed, x squared plus 3x plus 2 divided by x minus 7 minus m, which is 1, multiplied by x, right? And that is x squared plus 3x plus 2 minus x plus 7x minus x squared plus 7x over x minus 7. Limit equals, so x squared cancels, and we get 10x, so the limit of 10x plus 2 divided by x minus 7. We divide top and bottom by x, and we get 10 plus 2 over x, 1 minus 7 over x, limit as x tends to infinity. So this tends to 0, this tends to 0, and we get 10. So c is 10. So the asymptote is y equals x plus 10, as we already established. Okay, I'll stop here. I can talk about this for forever. I really enjoy this topic, and it's a really important one. I have done this webinar probably five times already, so you can always go back and see my previous recordings. I wish you all the best, and I'll see you next week for some very similar stuff where we do some inequalities. So enjoy, and I'll see you. Sorry, not next week, 2 weeks from now. Right. You're welcome.